as we think about the derivatives and how the derivatives can help us sketch the graph of f, if we don't know exactly what f looks like, we talked about how the first derivative has certain graphical impacts. The second derivative, so the derivative of the derivative, also gives us useful information about f. But then the first thing before we go into the details here, the interpretation. What would the second derivative mean? Well, it would be, and if we think about the derivative, right, it would be the derivative of the derivative, and that's the second derivative. So f is the rate of change in f with respect to x. So then what this would mean for us is it's the rate at which the rate of change, the instantaneous rate of change, IROC, is changing with respect to x. Okay, so it tells us how with respect to x. So it tells us how the rate of change is changing. It's kind of hard to think about, but what we can see is maybe some different language that can help solidify this a little bit. So there's kind of 5 different cases we're going to see. So first is, the intervals of increase of f. Okay, so it's intervals of increase. So we're going up. They're increasing at an increasing rate. So we're going up at a quicker and quicker rate. So something like this. Okay. Intervals of increase of f are increasing at a decreasing rate. So we're increasing, but we're slowing down. So something like this, right? So the slope is really positive here, becoming less positive over time. Okay. Number 3 says intervals of decrease of f, so we're going down, are decreasing at an increasing rate. So we're going down, but it's getting steeper as we go down, something like that. And so the fourth one is intervals of decrease of f are decreasing at a decreasing rate. So the slope is negative, okay, but it's getting less negative over time, something like, maybe exaggerate this a little bit more. So steep, and then it's becoming less steep over time, something like that. Exponential decay, if you were, okay? Or, we could have something that's not above, so it could just be intervals of increase of f are not increasing or decreasing, right? So it's just straight, right? So each one of these, if we look at them, they're measuring sort of a bendiness they're talking about a bendiness to the function, right? And that bending concept is known as concavity, okay? And so there's 2 different types of concavity that we see. There's concave up and concave down. So concave up is going to be a function that looks like it holds water. Okay, it makes a bowl. Okay, and I also want to emphasize that you could see either one side or the other side. You don't necessarily have to see both. Okay, similar thing with concave down. Concave down, I think of it as a hat. So again, you might see one side only, or you might see another side or the other side, or you might see both. Okay, but just know you don't have to have both present visually. So I'm going to make a little legend here. So I'm going to say concave up is going to be represented by a star, and concave down is going to be represented by an exclamation mark. What I want you to do is go back up here and identify which of these is concave up and concave down, okay? Pause the video, try it, and resume the video when you're ready to see the solution. So the first and the fourth are both concave up, right? This is the right half, this is the left half of that bowl shape, and then the hat, the concave down, is 2 and 3 because again you have kind of the left half of the hat and the right half of the hat. Okay, so just so we're aware about concave up and concave down, and so now let's think about what this is telling us. So if we kind of just have to go through this. We haven't worked too much with the second derivative yet, but if the second derivative is positive, then what we end up saying, and you might imagine what might happen, we're going to say f is concave up. Okay, so it makes that bowl. And if f is less than 0, then we're going to say f is concave down. Okay, and I also want to emphasize that when we talk about concavity, it has to be on an interval. Okay, just like increasing, decreasing, we don't talk about a point being concave up or concave down. Okay, so the last case that we have to consider, just like with increasing, decreasing, is that if the second derivative is 0 at a point, then we may have a point of inflection. And so just a point of inflection by definition is where its concavity changes. And it is a point, just to be clear too. Okay, now how do we resolve the may, right? What we need to do is check and see if the concavity does indeed change, because we could end up with, just like increasing, decreasing, how we ended up with a saddle in between, like it goes up and up or down and down on both sides. It could be concave up, stop, and then be concave up again, right? Or somewhere with down. So we would need to check to see that concavity indeed changes at this point of interest. And then after that, we can say, yep, it is a point of inflection. Okay. So now we have kind of some essential pieces of the puzzle known to us from the first and second derivatives that can inform how we generate the graph of f. So that's kind of where we're going to go, is in the next video, look at using bits of information about the first and second derivative to obtain a sketch of f.